Okay. Good morning, everybody. Yeah. Happy Makar Sankranti. So now we will be doing OS. Yesterday we completed the memory management techniques. Right. Like best fit, first fit, and worst fit. Okay. And now we will be completing the next experiments. And yesterday was a productive session, if I might say. All right. And let's get our ChatGPT opened. Concurrency, mental models. The CPU, laptop is already crying. Okay. FIFO. Alright. So the frames of I is allocated to -1 and found is initially set to 0. And if the frame is found, you just set the flag found to 1 and break it. And this is a break of if, and this is a break of in, therefore. And if it is not found, you are checking for every frame. If it is not found, you just frame of front. Okay. Alright, it is just like a queue. You just increment the front, alright. Technically, you're supposed to say it rare, right? I think. Let's see. Since we are using queue and inserting from rare. An honest question. We override frames. There is an explicit key operation. Yeah. So it is not wrong. Okay. Oh my god. Yeah, already gone through this data structures. Page replacement techniques. Page replacement techniques. Okay, today's Martin Luther's birthday. I see. Common input. One, 3, 0. 3, 5, 6, 3. Ballades anomaly. There are names for these, man. So, FIFO logic. Alright. The outer loop is going to go through 3 iterations, and for every frame, you are checking every page. Yes, that makes sense. And if the page is the frame, wait, for every frame, you are checking every page. No. This is different. Yeah, that's what I am thinking. This is different. This is just a lazy way of doing this. Frame setting -1. Right. So initialize pages frame n is equal to number of pages and frames is equals to 3. What is index? Right. Where did I read front then? No, I read front somewhere, right? I don't know. Is this the code that we are dealing? Yeah, I guess. I didn't even know where I read the front. Maybe rare is equals to 0, false is equals to 0. I have initialized all of this. Nice. For every page, found is equals to 0. For every frame, if frame is equals to page, found and break, it is just a flag. If not found, frame of rare is equals to page of I. Index is equals to index plus 1 mod frames false plus plus print frames and false. Nice, right? And about least recently used initialize pages, frames, and number of pages, number of frames, and false. Do you need index? Okay, wait. We just had a counter. Okay. If found, time, time of j or a time of j is equals to counter. Increment the counter right now. And if not found, least recently used is equals to 0. Okay. Get the least recently used. Get the least recently used. Okay. Frame of LRU. So now you got the least recently used. What's the idea? LRU replace the page that has not been used for the longest time. Okay. So what is it finding here? If not found, this block is important. If there exists a time, got it. So let's say the time is like 3, 2, 1. Then the LRU points to this one, and then LRU points to this one, and then this one. So this space gets replaced. Then what? Oh my god. Frame of LRU. Now you got the index of the frame that needs to be replaced. You are replacing it with the page. And you are incrementing the time of LRU. Because alright. I'm going to explain the LRU. Just give me a suggestion and more explanation. So the framework is same as before, just the what changes now? Replacement strategy changes. I mean, that's obvious. If the page is found in frame, we increment the respective counter of the frame. If not found, we find least recently used frame, and we replace that frame with the page, and we increment the time of that frame. Why are we incrementing the time? Okay. It's frequency. So I use its counter is 1, and now to remove and then turn to page again. Respond to reference 2 and its priority. Let's see. That's why talking out loud is important. Oh, it's already 15 minutes. That's a very good self explanation, Adam. Thank you. Okay, okay. If the page is found in frame, we increment the rest. We do not increment the frequency, we use the last year, we update the last year's time. Instead of thinking, alright, mark the frame as used now. This is recency. Not frequency, not priority, not how many times used. Yeah. Counter 1. First axis, second axis, third axis. Last axis order. When the page was last used. Time jail. This page was accessed at a logical time counter. Let's do a concrete try run. Got it. So these are pages, these are frames, and frame number, time, counter. Counter is equals to 1. Got it. Page 1 was last used at time 1. Oh my god. That's why counter is increasing even though you know if the page is found or not found. That's why the counter is increasing. Got it. Got it. Page 3. Okay, you used your time 3. All right. Page 3. That's it. Page 3's time did not change from 2 to 4. We did not increment. We replaced the whole timestamp. Wait, what? Okay. Page 5. That's fault. So 1 is not used recently. Okay. అడపెట్టే క్లాస్ రూమ్ అడపెట్టే
నేను పట్టుకుపోతాను అక్కడ ఉంటాయి
Oh my god. All right. Oh my god. Nah. That is making sense now. What is this all of you? Okay, I think we can do this. All right. Least recently used LRU. Pages were initialized. Frame was initialized. N is equal to 7. Frames is equals to 3. Have a time counter. Do you have any counter? Yeah, because you are just pushing in the frames. You are thinking frames as a queue and just pushing over there. That's it. I mean, if the frame is found in, if the page is found in frame, just put the found is equals to 1 and break. If not found, frame of rare, the rare was initially set to 0 because it is first in, first out, yeah. Um, I think we need to write that one. Yeah, because that improves the understanding, you know. Yeah, here. Therefore, pages inserted from rare removed from front. But there is technically no DQ operation. We overwrite frames in a circular manner. So both front and rear are unnecessary. Okay. Okay. Okay, I did not write the code here, my bad. Yep, LRU. Have a time array and have a false. Obviously, you need false. And this counter, this is our clock. I'm not writing this one, this is not needed. Alright. For every page, found is equals to 0 for every frame. If found, update time with counter. Time of j is equals to plus plus counter. Break it. If not found, LRU is equals to 0 for every frame. If time of j is LRU. LRU is equals to j. Frame, yeah. And now, what are you doing? Replace frame with base. And time of LRU. Increment time, like time of LRU plus plus counter. Why not time of j here? Halt plus plus. Print frames and faults. Least frequently used. This is same as least recently used. Mostly. So you have frames and you have frequency and you have faults. For every frame, increment the frequency and make it found and break it. Are we breaking here? Yeah, I found we don't need any further checking, so I break. If not found, what do we do? LFU is equals to 0. Nice. So obviously you have pages, you have frames, you have n is equals to 7 and frame is equals to frames is equals to 3, and you have frequency count initialize 0 because initially the frequency is 0. -1 shows not used and frequency is a counter, so it might start from 0. For each page found, it is a flag is equal to 0, and for each frame if found, frequency of j plus plus increment frequency found is equals to 1 and break. If not found, as well if u is equals to 0 is frequently used. For every frame, find LFU frame of LFU is equals to alright page of j, sorry, pages of I, yeah. So you replaced the frame with the necessary page, and you need to get the frequency of LFU is equals to 1. Got it. Fault increase, yeah. False plus plus. That's it. That is everything, and we will code. Processor 71. Wow. And what do we have? Yeah, we just need to check that, right? This one. So we are here, and we need to simulate paging and bankers algorithm and file allocation strategies. That's it. Simulate paging, bankers algorithm, and that file allocation strategies. That should be enough. Nice. Nano experiment 9.1.c. Right, so page replacement techniques. Since it is only simulation, we just need this one. Let's have the pages. There are 7 pages apparently. Okay, frame, yeah. We did not use any frames yet, so they are -1. And n is number of frames, that's 7. And frames is number of frames, that's 3. And rare is pointing for the queue counter, you can say. And false are initially set as 0. These are the initializations. Okay, you can initialize these in main if you want though, because you will not be using anywhere else, right? You know what? You can write the three programs with common data, but again they get modified, so I don't want to do that. I don't want to do that. Alright. So for every frame, I less than 7, I plus plus, and for every page, no, for every frame, you will be initially set found is equal to 0. And now for every frame, you can actually do that if you want. Wait, that's an okay. If frames of j is equals to pages of I, what do? You will set found is equals to 1 and you will break. And if you just loop through everything and in the outer loop, if not found, that is your flag. Okay, I want to look, I will do if not found, you just need to push it into the queue. Alright. How do you push it? Right? Frames, is it frame? Frame of rare. Yeah, frame of rare is equals to pages of I. I just pushed it and now you need to update the rare. Rare plus 1 mod. Where is this? Mod and frame. There is a number of frames, so it will be between 0, 1 and 2, and you need to increase the faults. Nice, and I think that's it. This is the outer if close, this is the outer for close, and now I will print the frames. Print frames, something like that, right? Percentage d \t frame of I. Nice. And then what do you do? Faults percentage d comma fault control x. Okay. Now what's happening? Okay. I don't know, I did something. .1 this is C, experiment 9.1.c, output file is experiment 9.1. Okay, Subscripted value is neither array nor pointer nor vector. It is frame of J. Okay. Okay, I missed that. Okay. Okay. At least we are able to read that. So we missed a semicolon somewhere. This is frame of 3. Here it is frame of J. Okay, that's good. And you missed a semicolon somewhere. And that one. Any missing semicolons here? I don't see any. Let's see. Now what? In the line 24. No, I changed that, right? Int main needs return 0. So let's do that. Int pages 1, 2, 3, 4, 5, 6, 7. Int frame n is equal to 7, frames is equals to 3. Right. Frames, yeah. This is if close and this is outer for close. I mean inner for close, yeah. This is if close and this is outer for close. Yeah, everything's seeming fine. Oh wait, this is for the braces also seems good. I less than frames, that's a comma. Okay. I less than frames, where is that? Here is the culprit. Okay. Alright. We forgot a backslash and again put a forward slash. So 5, 6, 3 are going to be the frames. Let's do a dry run. And it is saying, alright, 1, 3, 0. And again Alright, there is fault 1. No, there is no fault 1. 3 is hit. And 5, that is fault 1. How will there be 6 faults? Oh wait, these are 3 faults and that's 4. Nice, nice. That is 6 faults. 130 or put to 130. That's 3 faults for you. And 3 is already there. And 5 is not there, so that will become 4 faults. And 6 is not there, that will become 5 faults. The faults are 6, are you sure? Okay, Ubuntu is bugging for some times. Three zero three five six three. So 130 needs to be placed, and that's 3 faults. 3 is found. 5 is replaced with 1. So that's 4 faults. 6 is not found, that is 5 faults, but 3 is found, right? My doubt is why is 3 getting replaced? Okay. Let me check. One three zero. 3 is not a fault. 5 is a fault, that's 4. 6 is a fault. Alright. Yeah, 3 faults. Okay. 3 got replaced. 1 got replaced. Okay. It won't go there. Yeah. Yeah. Okay, got it. Okay. Let's compile it since we made some changes. Yeah, that's good. That's good. 54 minutes. Wow. And now we will do LRU, right? In frame of 3. Okay, 1303563. Yeah. You got n is equal to 7, frames is equal to 3. You need a counter. And you need the time. In time of 3, time is set to 0 initially. What is the time initially set to? I think you need that. Okay. All right. For every page, for every frame, you are checking if frame of j is equals to pages of I. Then what will you do? You will update the font is equals to 1, and you update the time of the frame, so time of j with the incremented counter. You will break because you found it, and if you did not find it, what will you do? Least recently this will be 0, and you will check for every frame if If there exists a frame of I is less than frame of LRU, you update the LRU with that. Now you got the LRU. Now you need to update that frame of LRU with the pages of I, and now the counter gets incremented. Nice, right? I did not see anything. Okay, okay, okay. Nice. That's for close. No, 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 no. That's if close and that's outer for close and render frames. For every frame, you will just print it. Frame of I. For every frame, you just print it and backslash n page faults faults. And I wrote everything without the main function. Congratulations. Now what will you do? GCC experiment 9.2.c output file is experiment 9.2. I opened it and I did not close it. Alright. Here. Where? Here, yeah. And there is no frame. And there is space here. Now what? Oh, come on, man. Okay, that is not there. Do we need to try on this? So that's 1, that is 1, and that is 3, that is 0. Alright. And the counter will be 1, 2, 3 for this. And 3 is there, and 5. 5 is not there. So that is 5. And that is 5, and that is 4, and 6, and that is 6. And now this is 6, this is 1, 3. Yeah, you have 3. So there are 5 page faults. 6, 3. Six, 3, 5. Let's try the value 2, please. 130, 3, 5, 6, 7. 3 recently used. Okay, 1 is replaced with 5. Then it will be 530. Okay, 3 is hit, right? You forgot to update the counter of 3. Yeah. 536. Okay, it printed in reverse. Let's see. No, why did it print in reverse? Time of J. Undefined behavior. Okay. We are still inside that, yeah. That's why understanding the scope is important. Got it. Frames are what? 536. Okay. It is just a coincidence. There are serious bugs in that. That's true. Paging bankers. Alright, we got 3 more experiments too. That's it. And we will write this. Let's try to write this. Inside the main, what will we be doing? We will initialize everything. Pages 130 356 3 frame of 3 now you need frequency count that is initialized to 000 and you need what? You need number of frames, number of pages, number of frames and number of faults. For every page, for every frame, you will be checking if pages of I is equals to frame of J, you will mark the found as 1 and you will update the frequency and you will break out of it. If it is not found, what will you do? You will have LFU is equals to 0 you will iterate through every frames for every frame if frequency of k is smaller than frequency of LFU. If that's the case, you will update LFU with k. Okay. You updated LFU with k, now you got the LFU. And now frame of LFU is equals to pages of I, and you will increment the faults and you will increment you will change the frequency LFU21. Nice, right? And that is if close, and that is outer for close. And frames backslash n. For every frame, you will be printing it. That's it. I feel like that should be enough. What? Okay, GCC. You always do that. J, right? Yeah, we're here. All right. Can you try around a few to 630 and 5? Ah, okay. Check empty frame. If no empty frame, then apply LFU. Okay, so here. So the scope of J is over, right? If the frame of J is equals to -1, LFU is equals to J, break. So there is no empty frame. If LFU is equals to -1, okay. But you cannot, write frequency of LFU now. All right. If you got a frequency count of J that is smaller than frequency of LFU, now you got the LFU. Okay, got it. And after that, what will you do? Now you got the LFU, right? Yeah. You will replace that frame. Frame LFU equals to pages of I false get increased. Frequency of LFU will be frequency of LFU will be what? 1. That's order for you. 1, 2, 3. Alright, you are informed. 1. Alright, that should be enough. Why do you always do this? Frames are what? 630. Nothing changed. I don't know why nothing changed. Right, let's check it. One tiny bracer. Even when I'm empty. Okay, even when an empty frame is found, okay, so if LFU you know what? If not found, LFU is set to -1. You are checking for empty frames. You broke it. I don't know. Okay, this is the block. FLFU. That's for close and that's if close. Yeah. But I'm getting this. Okay. Yes, that is required. Right, that was not wasted. And now simulate paging technique of memory management. Now we need to- that's it. You have page size, alright. Page table. Okay, that is easy. That's for sure. And how about this? The banker's algorithm. Okay, sorry. We should be able to do this. I'll be back in a minute or two. All right, we are back. We just have three experiments now. Three means five technically. Let's see. Okay. I guess this length is enough, right? Yeah. A computer has main memory, okay. Which process gets memory? Strong states address measured by programs, interaction, memory locations. When a program runs, it uses addresses to access memory. Logical address. CPU starts from zero, okay. Physical address. Actual address in RAM used by the hardware. This conversion is called address mapping. Before paging, memory was allocated as one continuous block. External fragmentation. Paging is a memory management technique in which logical memory is divided into fixed size frames. Oh, what? Alright. Physical memory. Pages are shown non-contiguously in frames. Page table. Page number and frame number. Page number and offset. I know what offset is. We calculated that before. Oh my god. Page number is a logical address by page size. Okay. Let's say LA is 250. Page size is 2. Then page number is Yeah, it will be 125. Offset is logical address mod page number. It's 0. So 125 times 2 plus 0 is equal to 250. So similarly, if you got 300 and something like 4, then the page number will be 300 by 4. That makes sense, right? Okay, it is exactly divisible. How about 10 and 297? That will be 29, and offset is 7. Nice. Physical address calculation. Extract page number. We just did that. Right. Page 2, frame 1. Frame number. For the page number, the corresponding frame number is 1. Okay. It is not present in memory. Must load it from disk. It is called page. Any external fragmentation. Alright, I understood the theory. Now let's see if we can understand the code. Okay, Banker's algorithm looks something big. Allocation matrix, maximum matrix, available resources. Calculate need matrix. Yeah, we need to know some other things for Banker's algorithm. Absolutely. This is page size. So this one, logical address, this one, page number, offset. These are something you calculate, and frame number is what you get at the end. Physical address. You got a page table 5621. You got the page size, that is, and you got the logical address. Page number is calculated and offset is calculated. Frame number, page table of page number. Okay. And the logical address and page size should not be 4 times bigger. Got it. And frame number is page table of page number. Okay, physical address is frame number. Nice. Oh my god. I kind of understood it. Let's write the algorithm and then let's code it. Alright, I'm so done. And then banker's algorithm is kind of big. And that's it. Nachos operating system. Okay. Oracle. So shall we write it? Yeah. Simulating paging. What will you do? Take page size, logical address, page table, maybe 5612. Page number, and offset, mod, and frame number, page table of page number, and physical address, frame number times page size, no, page number. Yeah, page size, sorry. Plus offset, show everything, and precautionary, yeah. We should be able to code this one. I mean, it's as simple as simple interest. So here should not be greater than having that said, enter away ampersand logical address. Alright, you got the logical address and page size. Now you are calculating page number. Logical address by page size and offset. Now you got it. Okay, you need to have a page table at the top. Okay, that checks out. It's our page table. And now frame number is equals to page table of what you calculated offset. No. Page number. Yeah. And now you got the frame number. PA is equals to physical address is page size times frame number plus offset. Nice. Printf page number is %d \n page number offset is percentility, max margin, output. Frame number is percentility. That's it. Nice. What is logical entry? Logical address, let's say, is 200 and right. Is this correct? Let's see. Right, we are good. Yeah, we are good. And now, banker's algorithm it is. Resources. Oh my god. We are down 2 hours and we did these 4 experiments. And we can do this. And we just got 4 experiments remaining, that's it. Deadlock occurs when each process is waiting for a resource. The resource is held by another waiting process. P1 holds printer and waits for scanner. P2 holds scanner and waits for printer. Both wait forever. Prevention, avoidance, detection, and recovery. Banker's algorithm is a resource allocation algorithm that checks whether granting a resource request keeps the system in safe state. Like a bank that lends money, the bank gives loans only if it can satisfy all customers eventually. Otherwise, it refuses the loan. A system is in safe state if there exists some order of processes such that each process can complete using available resources. Banker's algorithm never allows unsafe states. To decide if device needs extra data is stored. Allocation matrix shows how many resources are currently allocated to each process. Number of instances of resource J by process I. Okay. Shows how many resources are currently free in the system. Find a process whose need is less than available. Assume it finishes. Reduce its allocated resources. Got it. Nice. That's it. This is easy. We can do this in another hour. So we got N and M, an allocation matrix, maximum matrix, a need matrix, all of same dimensions, a number of available processes. Finish. I think the number of finished processes. The save sequence. Okay, we got number of processes, we got number of resources. Maximum matrix, we got it. Available resources. That's a one-dimensional array. Alright, need matrix. There you go. Maximum minus allocation. You got the need matrix. And what is count here? Count is less than n. Alright. Count is less than n. Found is equals to 0. Alright. Okay, we did this already. And for every process, that's it, right? Number of processes here. For every process, if it is not finished, and for every resource, if the need is greater than availability, break. Heart of the bankers algorithm. Uh, Keep trying to complete process until all are finished. Okay. Pessimistic assumption. Got it. Check each process one by one. Ignore already completed processes. If it is not finished, inner need versus available check. If the need is greater than allocation, break it. Did we check our resources without breaking? Okay. For every resource, if j is equals to m, what does it do? We check our resources without breaking. J gets incremented, right? Yeah. If j got to m, that means this never happened, right? Simulate process completion. Pretend this process has completed and release resources. Available. Allocated resources. Okay, got it. Record save sequence. Okay, it kind of clicked, and now let's make all the parts click up. Max need allocation. There are three matrices. The loop behavior is important. While count is smaller than n. Okay, let us assume it is not found. Pessimistic behavior. For every resource, if it is not finished, right, that means every resource can be allotted. Right. Simulating, alright. Availability, you are just increasing the availability of each resource. Right. Save sequence. Save sequence count is increased. Finish. Oh my god. Yeah, this is our pretty bankers algorithm. You got this, you got this, you got this, you got this, you got this. You calculated the need matrix, you got this one as well. What is count initiated to? Count is initiated to 0. So you are checking for every possibility. Found is 0. Okay. Assuming nothing's found. For every n is the number of processes. For every process, if it is not finished, if it is not finished, right, for every resource, if they are available, simulate work, freeze the resource. Increase the save count, maybe we should do something like this. No. If they are available, simulate. Release the resources. Here we are, and increase the save sequence count. Okay, what does save sequence track? I is the process index, right? Finish. Okay. Yeah, it returns the control. It won't ever come here. Okay. Save sequence. Okay, it prints this. Yeah, here is the return control. Let's say save sequence is an array. Save sequence and count is initiated to 0. That is one process, three process, two process, and four process. Let's say we have this save sequence count now, and you will print it. Okay, this is the found flag that helps not to return here. And finish of yes, the standard way. Okay, thank God. Yeah, that's not too bad. That's not too bad, to be honest. Alright. We will mess up with the looping variables mostly. But let's try it. Should we try it in the afternoon or now? It's 2 hours 26 minutes, alright. I will try it in the afternoon. I will take an hour break. I don't feel like taking break, man. That's the problem. I will code this. I'll code this. Okay, you know what? The code for bankers also. Yeah, look. Need max. Have NM. This is processes. And this is resources. Have the vector available resources and finish resources. Save sequence. What does finish is equals to 10 0? Let's see what it is for. Get n n alloc max. Okay, calculate need. Count. Didn't we initialize count? Where the heck is count? Okay, yeah. Count is equals to 0 while count is less than n for all resources. I mean for all processes. For all processes, found is equals to 0. This is going to be the flag. And for every process, if not finished, if need is greater than available for all break if j is equals to m, that means break never happened for every, what is m here? For every resource avail of k plus or is equals to log ik. Okay, okay, and save sequence count plus plus is equals to y. Post increment, if you check it out, finish found equals to 1. If close for close while close you found the save sequence. If not found, unsafe, return. If found, just print the save sequence. It is not working for some reason. Print save sequence. Okay. Oh, we got experiment 10. Yeah, where is experiment 10? Here. Anyways. That is enough. Yeah, let's experiment it. Oh god. Have the allocated matrix. Okay. And have the need matrix. And have the max matrix. And have the N and M. Right. Count initiated to 0. You need to have the tuples too. Available resources and finish. Okay. Why is finish initiated to 0? Simulation marker. Wow, this and all processes are initiated to 0. Save sequence of 10. Print and the number of process. ampersand. M is what? M is number of resources. Okay, allocated matrix. It is for processes, right? Ampersand. Alloc I J. That's it. Yeah, I guess. What now? Need matrix. No, not the need matrix. Not the max matrix. Max. Need of I J is equals to max of I J minus L of I J. While count is less than n, that is a flag, and for every process if it is not finished. Finished is a vector. For every process, if it is not finished, if need is greater than available, need of I you need two looping variables to access that, right? Yeah. Hmm. Really? Yeah. Okay. A process is allocated with resources. So that's what I expected. Available resources. So M is the number of resources, right? We had the available resources and calculated the need matrix. For every process, if it is not finished, okay. So for every resource, say sequence If it is not finished, for every resource, if need is a two-dimensional matrix, the need is greater than availability. Break it if j is equals to 10. That means break never happened for every resource. So availability. Okay, you are using available here. No, increase availability. Just incrementing the availability. If not finished, and if everything's alright, so now you need to save sequence. Still, it need to be inside the loop, right? Yeah. We're just having the order of processes and finish. And this is here. Wow. 1, 2, 3, 4. 3 braces needed to be closed to close the while, I see. So this closes. If not finished, okay, this closes this one. These two closes these two, and this closes if not finished, and this closes first. So we are inside count is less than equals to n. Oh my god. If it is not found, print the sequence is unsafe. Return. All right. Okay, that's 3. Nice. Did we come out of while loop? Yeah, I think we came out of while loop. What are we printing? Save seek. I spotted it. It will have many errors, don't worry. It's void, right? You don't need to write it. Just check the core logic once. Okay, resource release is wrong. It overrides available resources. Okay. You need to use this. Okay. Yeah, not that bad. Oh my god. N is equals to 3. N is equals to 2. Allocation matrix. 100111. Huh? 3, 2, 1, 0, 0, 1, 1, 1. Wow. That's what I wrote, right? Maybe flush out. Yeah. 211. Nice. Yeah. Okay. All right. What? P2. Okay. 1. Okay, got it. Change the P2. Kind of understood. 0, 0, 1, 1, 1. Hmm. 1, 0, 0, 1, 1, 1. What's happening now? Okay, that's my brain messing up. Enter the number of, that is 3, that is 2. Nice, that worked out. All right. I'm going to take a break and bye.